In this video, we're going to be talking about real-life applications of accumulation functions. So just like that, we have previously learned that the integral from a to b of the velocity function, v of t dt, can tell us the net distance of an object. When we take the integral of a derivative function, so in this case, a to b of f prime of x dx, that's equivalent to just a reminder of our fundamental theorem of calculus. That can tell us about net change. So I'm just going to write that out as an equation here just to see that. So basically the definite integral from a to b of f prime of x dx is equal to f of b minus f of a according to the fundamental theorem of calculus. We could rearrange that equation a little bit because in many questions, you're going to be asked to identify the end amount of some sort of application. So the end amount in this case is f of b. So if I just rewrite this by adding f of a to both sides, we basically get this variation of that equation. So the end amount is equal to the initial amount plus net change, or f of b is equal to f of a plus the definite integral from a to b of f prime of x dx. So let's practice writing some equations using that idea. Let's take a look at number one. So number one says a highway has heavy traffic due to construction. The rate at which cars pass a certain point on the highway, t hours after the project begins, is modeled by the function c of t. That's measured in cars per hour. When the construction starts, there are 50 cars already on the highway. So as I'm reading, I know that this is basically my initial amount. And then it says, write but do not solve an equation that involves an integral to find the time x where there are 300 cars on the highway. So we're trying to work with the end amount of 300, basically determine when that happens. So the end amount is 300. The initial amount was 50. And then basically what we're going to do is we're going to write an integral to talk about how the number of cars on the highway has changed. So we started with 50. That was at time t equals 0, okay, at the very beginning. We're trying to find a time x where there are 300 cars, and c of t dt can help us write that equation. So when we look at this here, we have 300 equals 50 plus the integral from 0 to x c of t dt. As a reminder, when you're writing these, this is our initial condition. And the initial condition has to do with whatever your lower bound is. So that's like what we know about the function, whereas the upper bound is basically what we want to know. And in this case, we want to know that time x. All right, let's take a look at another one that's similar. An airplane is flying for a 3-hour flight. The rate at which fuel is consumed by the airplane t hours after takeoff is modeled by the function f of t, measured in gallons per hour. At the start of the flight, the airplane has 10,000 gallons of fuel. So as I'm reading, I'm just going to mark that that's my initial value. And we're going to write, but not solve, an equation that involves an integral to find the time x where the airplane has 3,000 gallons of fuel remaining. So that is our end amount. So we're going to start by putting that over here. So we want to determine the time x where that occurs. The initial amount is 10,000. And when we do our integral here, we're going from 0 to x of f of t dt. The difference between question 1 and question 2 is that when we are writing this equation, we now need to put a minus between here. So we are starting with 10,000 gallons of fuel in this airplane, and it is losing fuel, right? We are using up the fuel, so it's decreasing. So we need to put a minus in there to represent that. So if you take a look at those two answers for 1 and 2, in number 1, the amount of cars were growing on the highway, so we had to put an addition sign in there. Whereas in number 2, the number of gallons of fuel is decreasing, so we have to put a subtraction sign. Okay, for numbers 3, 4, and 5, I will be using my TI-84 calculator to do some of the calculations. All right, number 3, the rate of water consumption in a city during the 1990s in millions of gallons per year is modeled by c of t equals 15.5 e to the 0.02 t. T represents the number of years after January 1st, 1990. We're asked to find the total water consumption in the city during the 1990s. So total indicates something with an integral here, right? That's always a key word for integrating. And let's just talk about our bounds here. So if we're talking about the 1990s, that means we're talking about from 1990 to 1999. Now we know that 1990 is representing t equals 0. And that means 1999 is going to be represented by t equals 9 in this problem. All right, so now let's see if we could write our integral. So we are going to integrate from 0 to 9 of c of t dt. We could also write that by actually putting the function in there. So that's 15.5 e to the 0.02t dt. And then I'm going to go over to my calculator to determine that answer. So I'm going to go to math and then 9. I'm going to plug in my bounds. And then I'm going to plug in our function. For this, we're going to go with rounding rules of always 3 decimal places at least. So I get 152.843. And if we're talking about units here, right, when we're doing application problems, we should be thinking about what the units are. This is the in millions of gallons of water. Okay, number 4. The rate at which items are produced in a factory in items per hour is modeled by P of t equals 30 plus 10 e to the negative 0.03 t. P of t is the rate of production in items per hour. T is the time in hours since the factory started its operation. If the factory started with 1,000 items in stock, how many items are in the factory after 20 hours of production? So this I can tell is one of those questions like we did in 1 and 2 where we're basically working with an initial amount. So the 1,000, if that's how much is initially in stock, we're going to consider that our initial amount, therefore. And we're trying to figure out how many items there are after 20 hours. So our rule is basically the end amount is equal to the initial amount plus the net change. So we do not know our end amount. That's what we're trying to find. We're starting with 1,000 items in stock. And then to write our net change, we're going to do the integral from 0 to 20, because we're talking about over 20 hours, of P of t dt. Then over on the right, you can see I'm going to go to my calculator and go to math 9. And I'm going to evaluate that function. So I'm going to plug in for P of t 30 plus 10 e to the negative 0.03 t. And so now I can do some addition in here. So I'm going to be adding 1,000 to that. And of course, you could have put that 1,000 in the initial line and then added the integral. That's completely fine. And we're going to do to 3 decimal places. So that's 1,750.396. And we're asked for how many items in the factory. All right, for number 5, those of you taking AP Calculus, right, you're going to see questions like this when you are working on the free response questions. So this question's a little bit different because there are 2 functions given to us. So if we look at this here, it says cars enter a parking garage at a rate modeled by E of t, and we're given that function, and it leaves the parking garage at a rate modeled by L of t. Both E of t and L of t are measured in cars per hour, and t is measured in hours since noon. Part A says how many cars enter the parking garage from noon to 2. So that's from t equals 0 to t equals 2. And I'm just going to use the function that represents the entry. So from 0 to 2, that's 30 plus 10 sine pi of t dt. And I'm going to go to my calculator and integrate. And I get that there are 60 cars that enter the parking garage from noon to 2. Now, for part B, it says if at noon there are already 100 cars in the parking garage, how many cars are in the parking lot at 4 p.m.? So we want to figure out how many cars are there at 4. So that's when T is equal to 4. So we're starting with 100. It's our initial amount. We're going to add the net change integral in here. But we also have to take into account that cars are leaving from 0 to 4, from noon to 4 p.m. So we're going to also subtract the function that represents cars leaving the parking garage or parking lot. So I've gone ahead and evaluated the two integrals in my calculator. So I'm going to do 100 plus 120 minus the 162.666 and so on. And when we're done there, we get that there are 57.333 cars in the parking garage at 4 p.m.